taking a look at graphing a polar function. So to put it into polar mode, first we're going to do is we have to go to our mode button right here. So we select that. And for the most part, you need to be in radians mode for most things. So we can see radians is highlighted, so that's good. Then we go to this section right below that has function highlight. It's got a couple other options, parametric, polar, and then sequence. So we're going to scroll over to polar. We're going to make sure that's highlighted. So now we're in polar function mode. And now if we go to our y equals, rather than having it as our y equals when we type in functions of x, it's r equals. So we'll type in our equation the same way we would if it was an equation with our variable and everything. So it says 2 minus 6 cosine theta. So you do our 2 minus 6 cosine. And this button right here, see how it says x, comma, t, comma, theta, comma, n? That accounts for all 4 modes. So the third mode, polar, is the theta button. So when we press that, there's our theta. And if we graph that, it gives us our curve. Now, if we're trying to plot this by hand, is using our unit circle values, which can get very tedious, so we can use the table values to help us out. The problem, of course, if I go to second graph right now and look at our table, it's kind of all over the place. It's not really useful values there because it's our usual negative 10 to 10. So what we're going to do is we're going to go to table set. So it's second window. And then we want to still start at 0, but our table values with these are graphing our polar functions is going up by pi over 12. So that's what the delta table represents. So we're going to type in second pi, and then divided by 12. And we're going to hit enter. It's going to give a decimal equivalent to it. And now when we go ahead and hit our second table, these are now the appropriate values, where we're starting at 0. That's pi over 12, pi over 6, pi over 4, pi over 3, 5 pi over 12, pi over 2. And then next up would be our 7 pi over 12, 2 pi over 3, 3 pi over 4, 5 pi over 6, 11 pi over 12, and then pi. And we kind of keep on going through that. So we can kind of scroll, and that's how we're going to fill out our tables to make our graph, just recognizing each one is going up by pi over 12s. So those are different R values, recognizing what to do when R's are negatives. And again, when we take our graphs, we're just going to always go to the tenths place for our roundings because plotting, for example, 0.4471 is tough enough to plot 0.4, let alone all the extra nonsense. So we're just going to write out to the tenths place there. So I'm going to show you a couple other graphs. And it's kind of like, so we kind of scroll through here and how to kind of get ourselves back. So the next graph we have going on will not be, this was one of our limacons. This was a loop limacon. So you can see there's that inner loop right there. We'll take a look at some of the other shapes as well, especially the lemniscate. That's going to be our last example we take a look at. All right, so next up we have our rows here. And these are rows in the even value of n, which tells us there should be double the number of petals we have for n. So if n is 4, there should be 8 petals. If we hit our 5 cosine 4 theta, and we graph that, you can count and see there's our 8 petals we got going on there. Now, if we're looking at the table of values, you'll notice, because we had scrolled last time, we're not starting at 0 anymore. We're starting at wherever we had last scrolled to. So if you want to always go back to 0, depending on how far you scroll down, second table set, table start, make it back to 0. Delta table is fine. That's not going to change until we tell it to change. Something to keep in mind, if you are going to graph in a different mode, you are going to have to go back and fix this, because this will be the delta table you use for every single graph until you've changed it up. So we go ahead back to second table, and now we're starting at 0 again. All right, so this one's our rows with an odd number. So if we see here, there should only be a total of 3 rows petals for this particular graph. Again, it doesn't matter that it's sine or cosine. That part's not relevant to the number of petals. It's the value of n that we're learning about, concerning ourselves with. And you can see, there's our 3 rows petals. Second graph still gives us our table of values we can work with. Again, still starting at 0, going pi over 12, pi over 6, pi over 4, pi over 3, and so on down the list. Now, the last one we're going to take a look at is the lemniscate, and that's going to be a little more interesting because of how the equation is set up. All right, so we're going to take a look at the lemniscate here, which again, as you can see, the equation is based on r squared. So we can't graph r squared. We have to rewrite it as the square roots. So we do our square roots, 36 cosine 2 theta. Doesn't matter whether it's cosine or sine, it always has to be a 2 theta for this to work. If you look at the actual graph, we know this is supposed to be the infinity symbol or like an 8 loop, that kind of stuff. And we see certain stuffs are cut off from there. That's just kind of due to the nature of this particular, we're taking the square root. We have to watch out when there's square roots of negatives. And since we're doing decimal approximations going there, it's kind of messing up certain spots. So you can't really rely fully on the actual graph. Do you want to talk about what the table does look like though? So if we look at the second graph, you see our y values. We have some nice y values and we have error messages because those are where we're taking the square root of a negative number. Because again, unit circled, cosine's negative in the second and third quadrants. Now obviously the angles are not matching up the second and third quadrant because it's 2 theta though. So we have to account for that possibility. So there's 5 of them. And then this number right here is supposed to be a 0. When it gives us that weird scientific notation with like e to the negative something, that's just 0. So that's our 0, 4.24, 5.5, 6, and then 5.5, 4. Now this is error right here, but this is actually supposed to be a 0 because this is what the pattern is supposed to be. And that's kind of why the graph was kind of a little bit messed up. It didn't really show the correct point here because since it's doing a numerical approximation and it's not doing the exact, so this should have been, let's see, this was, the 6 was at pi, it's 13 pi over 12, 7 pi over 6, 5 pi, this should have been 5 pi over 4. And that should be a 0 there. Because if you think about it, 2 times 5 pi over 4 is 5 pi over 2. Cosine of any pi over 2 is going to be a 0, so that should be giving us a square root of 0 here. But with the decimal approximations going on, it probably gave us a value that was a little bit bigger than 5 pi over 2, like ever so slightly, which would have then caused a situation where it creates a negative inside there. So you have to recognize the pattern is supposed to be a 0, some 3 numbers, and then kind of repeating that pattern from there. So this should have been a 0. That's correctly an error, 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 error. Let's see, there's too many errors here. We skipped over 0 again. So this spot right here should have been a 0. So there's always supposed to be a 0 before you start getting to the error messages. So you have to be very careful when you're looking at your tables for that particular reason. There's only supposed to be 5 error messages, whether it's cosine or sine. The zeros for cosine should be occurring at the pi over 4s. And then the errors are going to be in between them. Whereas for the sines, the errors should be occurring at the pi's and the pi over 2s. That's where the errors should be occurring for the sines. Or sorry, the zeros. So then the errors are in between them. So that should be a 0. Then there are 4, 5, 6. And I believe then we're off the grid at that point because this was 2 pi. All right, so that's what we're looking at for our polar graphs. Again, using the calculator to help you. If you want to do it all by hand, you certainly could. There's nothing wrong with that calculation. It would just be a little tedious calculating that many particular points.